I'm very excited that he's giving his talk today on cosmological emulators for high-dimensional inference. Thanks, Matt.
Thanks a lot. Yeah, I really appreciate you guys invited me to give a talk. I think this is my first time talking to a little broader audience and other than astronomers about what I do with machine learning and cosmology. So yeah, if I'm wrong in some aspects related to statistics and stuff like that, yeah, please correct me. I would appreciate that. So yeah, so this is our collaboration. So we have here I work with HETDEX, which is a galaxy survey. So far, it has observed around 2 million galaxies around cosmic noon. And the goal is to use a clustering of these galaxies to learn about cosmology, like how the universe is expanding and a lot of other parameters that we are interested in. Here are the two collaborations. These are from my grad school. So basically from the theory side of it, Priya and Goku. These are a suite of simulations designed for modeling lime alpha forest, which is basically gas in a galactic medium. And also kind of related to HETDEX, the last one is embodied simulations, which are good for modeling the galaxy clustering. And I'm using Goku for modeling what the signal in HETDEX. So a lot of work is from the collaborations I try to cite when I'm talking about a particular project, but yeah, it's teamwork. Okay, so what is cosmological inference? The challenge we have is we have very high dimensional parameter space. We want in astrophysics, we want to change a lot of these parameters and run one simulation for each parameter and then see what would be the observable. Then you compare it with the observation to infer the parameters you are interested in. Usually these are high dimensional. Here I have listed 9 from the Lime Alpha Forest project. A lot of them are astrophysical parameters. Some of them are cosmological parameters. And basically you run one simulation for each set of these parameters and then compare it with the observation. The simulations are expensive. Basically, it is impossible to evaluate the model at each MCMC step, so you cannot do the inference directly using the simulations. That is why you need machine learning. Yeah, the solution is to basically train some machine learning models. They are called surrogate models because they try to approximate the actual simulations, or also called emulators, to model these summary statistics we are observing with different surveys. This one is an example from the Lime Alpha Forest project. Basically, each curve is one summary statistic coming from different epochs in the universe. So the goal is to model the summary statistics using machine learning techniques and our simulations. So what emulators do, they model the true underlying summary statistics. So the summary statistics could be probability distribution function of objects you're observing. It could be power spectrum or two-point correlation function. They can also be neural nets, which are compressing field level information. Then the weights of your neural net are going to be the things you are trying to model. So these are two examples, the power spectrum I just mentioned from Lime Alpha Forest and the probability distribution function over the mass of the galaxies you're observing. By true, I mean, we are trying to understand what is the underlying summary statistics. We form a likelihood to infer these parameters. So basically a standard likelihood is going to be like this. You have a Gaussian model. You compare your model, which is coming from the emulator, with what you're observing, and assuming a covariance, which is usually data-driven. So you get the data and covariance from your data side, and you have your model coming from your emulator and your theory. You form the likelihood, you have some prior, and then you infer the parameters. So that is the standard inference pipeline we have using the emulator. So here we assume this formal likelihood and getting the data and covariance from the data. And then theory is kind of separate from what you have from the data, and then you have form the likelihood. The alternative is doing likelihood-free inference, like what we've heard the last few weeks. So by free, it means there is no assumption on the likelihood. So in previous page, when we had the Gaussian likelihood here, for likelihood-free inference, you don't have any assumption for the likelihood. So it means you don't need the covariance. Therefore, you need to forward model all the observational effects you have on your theory. So basically, you form some mock observations. You have your simulations. You apply all the observational systematics and noise you have on the simulations. You make these mock catalogs, which kind of are similar to what you're observing. This example is from Simbic collaboration for the Boss Galaxy survey. So when you're observing, there are like patches of the sky you cannot observe because there's already like a big galaxy nearby, stars, and so many other things. So this likelihood-free inference approach, it is kind of like mixing the theory and the modeling for the systematics. So you make these mock observations, and you have your actual observations. Then you have a way of comparing these two, which is basically having a loss function, comparing these two, and then you infer the parameters. So it is kind of like end-to-end pipeline for inferring your parameters for a particular observation with a particular systematics. So I have some concerns about this, which these are like probably like my concerns. Maybe people have like different opinions about it, but I kind of find this a little bit hard to interpret when you're mixing what your theory is predicting with what you're observing. Basically, it is hard to distinguish where your machine learning model is failing in approximating what the theory should be, and basically with observational systematics. So one aspect is I kind of feel it might be hard to interpret the result. The other thing is for modeling the systematics on your simulations could be expensive. So if you have simple systematics, like putting simple cuts on the data and things like that, it would be easy to forward model these on your simulations. But if it is a little bit more complicated, which I'm going to talk about HETDEX later, this would be really computationally challenging to apply on all your mock catalogs. For example, for HETDEX, each patch of the sky has very different systematic based on like the observation, observing conditions of that night. So you need to apply different conditions on many mock observations you have. So like when you do the number, it is a little bit challenging computational wise. Now I'm going to talk about our emulation technique. We are using Gaussian process. Probably a lot of you have heard about my Gaussian process, but I'm going to just like give it a very quick introduction. So with Gaussian process, it is a non-parametric way of fitting data. And also at the same time, you constrain your uncertainties. So basically, it is a probabilistic model to fit functions with constraining the uncertainties as well. So if you have a one-dimensional function, theta is only one dimension, not 10 dimension. Imagine you have only one, and f is the value of the function you're trying to model. What Gaussian process is basically, if you just sample a finite collection of these data points along theta, the probability over the values the functions can have is coming from a multidimensional Gaussian distribution. And if you just this is a stochastic process. If you go to the like continuous regime, then you have this Gaussian process modeling the family of functions can satisfy these observed data points for your function. So here, the parameters you are going to learn, these are the hyperparameters you have in your Gaussian process, which is basically mostly this kernel you have, which describes how these parameters are correlated with each other. These are a bunch of examples of the kernels. The one that quite often uses this RBF kernel, which is basically a Gaussian distribution. So here it is an example of two-dimensional parameter. So for this, you have a Gaussian distribution, and then when you get further from this diagonal terms, it just vanishes, and you have like a bunch of other parameters. So all of this, they have a bunch of free parameters. Like for this RBF, you have L, which determines which is the typical length of the correlation for each parameter. So if L is just too large, it means that parameter doesn't change when you're going from a low value to the high. That parameter, when you're going from a low value to a high value, doesn't affect much your observable, the function you're trying to model here. But if it is like smaller, then it means when you're changing your parameter in that direction, your observable is changing quite fast. So there is like some level of interoperability of the free parameters you have or the hyperparameters you have in the kernel. But basically, these are the thing you train your machine learning on, and you're trying to learn these hyperparameters. So the particular approach we have is multi-fidelity Gaussian process. It is quite popular method in physics to model whatever observable you have. So trying to fix this, yeah. My grad school friend Minfon worked on this, basically applied this method in cosmology, which we have been using since then. The idea is you have many low fidelity simulations, which are cheap. You can run many of them. So they're kind of the labor, they're exploring the parameter space. So you have, you learn the function you're trying to estimate, like the summary statistics with these many low fidelity simulations. And you have high fidelity simulations, which they're a little bit more expensive. So you can only run a few of them, but you need them for correcting the resolution effect. So these guys, low fidelity ones, explore the parameter space. The high fidelity one, you only have a few of them, and that's the level of accuracy or level of precision you want to have for your modeling. So the goal is to get to the accuracy of the high fidelity without running all the high fidelity simulations. The low fidelity will do a lot of work. So here I have an example of that. There are two type of low fidelity simulations. The L1 is, so you have the high fidelity here. The L1 is a low fidelity with the same box size, but it has lower resolution. So in total, you have less particles. So it is easier to run them, still cheap. And the other one is you have a smaller simulation, but with the same resolution as the high fidelity one. So basically this low fidelity one, L2, with the small box high resolution, it captures the smaller scale features, but misses information on larger scales. And the other one captures large scale information, but misses information on small scales. So combining these three, you can train your emulator to achieve the high fidelity accuracy. So this is kind of like the summary statistics showing this. This is a power spectrum, which shows shows the strength of a signal at different scales, the strength of clustering at different scales. As you go to higher case, you're looking at smaller scales. So when you look at here, this is the high fidelity one, and L2, which has higher resolution, but the L1, because it doesn't have enough resolution, it is deviating from the high fidelity one. Sure.
So in terms of the high and low fidelity, they have exactly the same physics, just different resolution?
Yes, it's exactly the same physics and exactly the same initial conditions. So if you look here, you see the same features here, and you see it in high fidelity as well.
I was wondering, in the case where you have feedback, depending on the resolution, the feedback might interact very differently, right? For example, the porosity might be affected strongly. So I'm wondering, like, how generalizable this is for cases where the physics is a lot more difficult.
That's true. Yeah, so the kind of feedback models we had in the case of line alpha forest, which it was full hydro, it was agent feedback. So we didn't have much, it wasn't too much dependent on the resolution. As long as you have enough resolution to have the galaxy, then you can have the feedback. But yes, it is going to be important if you're having stellar feedback in your galaxies, then how much resolving power you have for the ISM definitely is important. Yeah, I think we haven't explored that for the kind of feedbacks that are resolution dependent. Yeah, here basically the ratio is a little bit better to look at. The L2, what we have here, oh yeah. So this one is L1 to HF, the big box. It is failing on smaller scales, while it is good at at larger scales. And the other one, L2 here, is failing on larger scales, while it is good at smaller scales. So basically, having these two types of simulations help us to explore the parameter space and make it much more computationally. So there are different kind of multi-fidelity technique you could have. One of them is Kennedy-O'Hagan model or the linear multi-fidelity model. So in this, you are getting the high fidelity level result by scaling the low fidelity one and then adding it by a bias factor. So here the FLF is the posterior you get from a Gaussian process trained only on the low fidelity one. And then you scale it by a simple scalar factor. And then any residual cosmology dependence is modeled by this bias factor. So if your low fidelity and high fidelity are close enough that you can just like get the make a map from low fidelity to high fidelity by a scaling and just a small correction factor, then you can basically use this linear multi-fidelity model. But if the map from low fidelity to high fidelity is very nonlinear, then you need to make a nonlinear map between them, which is another Gaussian process. Here, rho is another Gaussian process, which depends on the posterior values coming from the low fidelity one and also cosmological parameters. And also, you can still have the bias factor to model any residual effects. So for majority of the cases, we found linear multi-fidelity was good enough. But there are cases if the mapping is very crazy, then probably you need to use something like the nonlinear multi-fidelity model. Yes. From now on, I'm going to talk a little bit about the applications. So the cool thing is, after we trained these machine learning models, we ended up actually using it for inference, which is nice. Most of the times, you just stop after training your machine learning model. Here, I'm going to talk about line map forests. Basically, it is looking at the clustering of inner galactic gas. You have many lines of sides. They are just like passing through the universe. And here it is, you have a map of the gas or like galaxies in the universe. So you have many line of sides passing through the gas. And along this line of sight, you have some features which are basically tracing the amount of gas you have along each skewers. So, and if you take the power spectrum, which is basically constraining the amount of clustering along these line of sides on different scales, you would get this observed power spectrums, which has been observed with STSS. So this is the summary statistics, how much clustering you have along these line of sides. And what we want to do is take these summary statistics and see what was the underlying cosmology that got us this power spectrum. So here we have the multi-fidelity model. In this case, we didn't use two multi-fidelity models. It is only one, so the same box size, but with different resolutions. One of them is high resolution, the other one is low resolution. As you see, like qualitatively, the low resolution has high resolutions that they are different at some places, but overall they match. And when you look at individual signal along line of sides, there are places that they are a little bit different, but still they are a good basic price of each other. So what we do here, we have like a very nonlinear multi-scale physical processes going on. As Asila said, like feedback, you have galaxies forming, you have supermassive black holes, they eject heat, they eject stops into the inner galactic medium. That's one part, the astrophysics. The other astrophysical like parameters we have is how like the universe got ionized when when the universe is evolving. Because galaxies are forming, they just radiate a lot of photons. They go into intergalactic medium, they ionize photons. So when this process happens, it's kind of not fully constrained. So we have parameters for those. And also we have a bunch of cosmological parameters, like how much matter you matter initially you had in the universe, and also how fast the universe is expanding, and stuff like that. So it is high dimensional parameter space. For the line alpha force, we had 9 dimensional parameter space. We trained 6 low fidelity simulations and only 3 high fidelity simulations to achieve kind of person level accuracy for modeling the power spectrum. Here, if you look at the yellow distribution, this is the distribution of the errors we get through the leave one out test. So in this like cross validation, we leave one of the simulations out, one of the high fidelity simulations out. We train the emulator on the remaining simulations and test it on the one that is left out. So this one shows the distribution, and we get person level accuracy in terms of modeling the signal that the emulator hasn't yet seen. The cool thing is with this emulator, because you're kind of modeling the underlying truth signal, you can see what kind of parameter sensitivity you have. So your learned kernel is learning about like these parameter sensitivities and also degeneracy between these parameters. For example, here, as you change one of these parameters, amplitude of this initial power spectrum in your simulations, your observable is changing. And also, as you see, there is a scale dependent, there's a slope, there's a scale dependent change with this parameter. And same thing happens with another parameter, which is kind of still related to power spectrum, but another parameter. And also some astrophysical parameter has similar scale dependent effect on the power spectrum. So the cool thing is you have learned the kernel. So from the theory, at least from the theory, you know how these parameters have degeneracy with each other. So going to actual application on the data. So I've been showing these plots here. These are the observed power spectrum of the Line-Malfa forest. Martin, he was previously in my grad school group, but now he went to climate science, but he did a cool project, wrote this paper applying our emulator on actual observed data. So we use the CSS power spectrum, form the likelihood, then basically run MCMC to infer the parameters. Here we have the posterior distributions, posterior prediction of the emulator versus what you observe. So your data points are basically these things with shaded region around them, and the colorful ones are the prediction from our emulator. We do a good job at for some of the data, and for some of them, our emulator could not like properly reproduce what has been observed. So it could mean like our model maybe is not good for these different data bins, which are basically different epochs of the universe, or it could be there's some systematics in the data that we still need to understand, so we could have like a proper uniform understanding of like the comparison between data and the observation. So this is the inferred parameters, this coordinate plot that cosmologists love. What it shows this basically after you run the MCMC, you can constrain this the parameters you have. So I'm not going to go into the details. That's why this is small, but I would be happy to talk about it. As I said, you can with the emulator, and now you have the observed data. You run the MCMC. You can see how these parameters are degenerated. So this one is shows the covariance matrix between different parameters. As you expect, the diagonal is the strongest, but you can see that there are degeneracy between other parameters as well. Like if you look at here, some of these are like anti-correlated, and basically none of it. Yeah, so there are some degeneracies between these parameters that you can actually see. So one of these parameters that turned out to be important is the ionization model I was talking about, which this parameter, alpha Q, is kind of like correlated with like alpha AP, which I was showing here. Yeah, this scale dependence of alpha Q and these parameters was quite like important in our inference for these parameters, which previously, because the previous simulations, they didn't have a high dimensional parameter space, they couldn't see these degeneracies, and the inference was kind of biased previously. Okay, so now I'm going to talk about HETDEX, which is the project we are working here at in Austin. We are looking at the clustering of the galaxies. It is kind of similarly mapping the cosmic density, instead of looking at the inner galactic gas, now we are looking at the true distribution of the galaxies. So far, it has observed around 1.7 million candidate galaxies, which probably most of them are actual galaxies. In the span of 7 years, there has been a lot of effort to get to the galaxy catalog so we can use it for inference. So you get something like this. There are like so many fibers on the sky. You have a lot of giants like satellites, stars, and things that you're not interested in. You clean up these observations. Then you look at for a small bump here, which is a galaxy, and we are looking for these small bumps across a lot of noises. So there is a lot of work to get here, and also when you get your source catalog, you need to classify them to see which kind of galaxies they are, if they are the Lyman like alpha emitters that you're interested in. So there's like the collaboration has a lot of code for doing this kind of things. Dawson and Aaron have developed a lot of things, and also Lindsay. She has been working on the citizen science project, which you basically give this spectrum to people and also some other imaging. Then they help you to classify if that detection is real or not. So for basically, it helps a lot to have a lot of training data. And using those, Aaron and Shiro, they have been working on random forest and neural network classifier to reduce the false positives you have, and also for the classification. So you have these, then you get a catalog of the galaxies. This is a footprint of the survey. It's a huge amount. It's a huge amount of data, and each data point you have here is one of these guys. So you have immense amount of data here that needed to be cleaned, and all of this are being done and have been done. Now it's the time to do the cosmology. So Owen is a graduate student here at UT Austin. He has done amazing work in estimating the galaxy clustering we are looking for. So as you see, this survey geometry and also you don't see the selection function here, but they're very complicated. So when you're calculating galaxy survey, you need to account for them. So how we are doing that is we pass a uniformly random data set through this pipeline, through the detection pipeline. So we see if you have uniformly distributed samples and the detection pipeline is picking some and not picking the others. Then from this, you get a sense of what are your systematics. So to estimate the true two-point correlation function, we are using the Landis-Allais estimator. So you have this random catalog that Owen is running are here, and you have the actual data. So this is going to be the pair count. So basically, you just pair count the data, and you subtract by twice of the data random pair, and then added random. There's a whole literature showing how this estimator is a good estimator for the actual correlation function. So by getting this random catalog and using the Landis-Allais estimator, now you have an estimation for the true underlying correlation function. So why we are not, as I said, we are not doing likelihood-free inference here, because there's systematics to just like run your catalog each time from the through the detection pipeline is very computationally expensive. So we can only do it like a few times for getting these random catalogs. Then when you have the random catalog, you rely on this estimator to estimate the underlying truth. Then you have your emulator, so you can model the theory expectations. Going back to the theory side, Yan Hui has recently put this paper on Goku suite simulations. So these are n-body simulations. So we don't have gas, we don't model the gas dynamics, only the gravity. We have crazy amount of simulations. We have around like 2,300 low fidelity simulations with a different box size and resolution. And also we have 36 high fidelity simulations. So the goal is to get to the high fidelity accuracy. Similar thing as I showed before, this is the power spectrum for the matter. As we see on small scales, these guys, which are the small box, the large box, low resolution, is deviating from the high fidelity, and here this small box, high resolution, deviates from the high fidelity because it doesn't have the large scale information as a high fidelity one. So what we are doing at the moment is to build the emulator for the galaxy survey. So what we saw here is the underlying matter power spectrum, which is a smooth density field. But the problem with the galaxies is they're discrete sources. So the resolution becomes more important. And also these galaxies, because they're kind of like biased tracer of this cosmology, they respond to cosmology more aggressively compared to matter power spectrum. So we need to, what we are doing now, we are building a new emulator, but only for the galaxy clustering, as opposed to what we had here for the matter power spectrum. So these are the parameters we are changing, and each blue point is a low fidelity simulation. So we have 10 dimensional parameter space here. The red ones are high fidelity ones. We used Latin hypercube to sample these parameters. You see a red box at the middle. We just ran, as maybe the color selection wasn't ideal, but there are boxes here. So on the top corner, you have same corner plot for these red boxes. So basically, the top one is zoomed in on these red boxes. So we ran more simulations around the prior region that we think it is more likely because it is around Planck, which has already constrained some of these parameters. So basically, we needed this narrow prior range to improve the accuracy of the emulator to get to percent level around the likely region of the prior. So here we are trying to model the galaxy HETDEX observables. These are galaxy clustering. Here, the Y shows the amplitude of the clustering and as a function of distance, and these are different cosmologies. We have been working on this. Sometimes it gets tricky because of these two effects I just mentioned. So it is a preliminary result here for the probability distribution function over the mass of halo mass of these galaxies. As you see, the theory and prediction, the solid ones are they're the underlying true coefficient function, and the dotted one is the emulator's prediction. They kind of follow each other for some cosmologies, but for some cosmologies that are a little bit outlier, the emulator hasn't seen enough cosmology to do a good job in terms of predicting the coefficient function. So yeah, there are a little bit challenges on this, but we are working on it, and hopefully we can get the same level of accuracy as we had for the Line-Alpha forest, and hopefully then we can use it for constraining the parameters. Yeah, I'm a little bit early. I finished early, but I obviously have the questions. But for the conclusion, we need percent level accuracy for the current non-copying cosmology surveys, because the goal has been to get there. With HETDEX, we have so many sources that we can actually get to those level of precision. So we can use emulators and run a reasonable amount of simulations using machine learning techniques like the multi-fidelity technique we have here. So we can use this emulator to do MCMC run and then constrain the parameters of interest. I think, yeah, that's it.
So we'll alternate between any questions online and any questions here in person.
Out of like the 2 million candidate galaxies that the was it HETDEX found, in your model, like how many what's like the success rate, like of those 2 million, how many ended up being real galaxies? And how do you confirm that it's a real galaxy? Like, can a human look at it? Can an astronomer look at it and tell you whether or not, oh yeah, that's a weird one, or that's a...
Yeah, that's a great question. I'm sure Aaron and Shiro, Dawson are better people to talk about this, but yeah, there are other ways. I mean, there's so many ways to do that. One of them is you repeat the observation to see if you get lucky and the sky is better and you can see some. And you can also use auxiliary observations like James Webb is also like observing some of these parts, and it's a bigger telescope, and also like it has longer, it's out like in space and longer exposures. So you kind of expect to see them with that. And also there are other surveys like dark energy spectroscopy instrument, like DESI. They also look for galaxies. And also you can use citizen science. People look at these bumps here, and then they have been shown a few examples of like the true galaxies. So they also help to get some training points for your like neural networks to do the false positive.
And if they're not galaxies, what are they like usually instead?
Yes, they could be like low redshift galaxies,
Okay.
or they could be other type of galaxies like AGN, or they could be also so as you see, the signal to noise for some of this is not that high. Some of them could be noise. So yeah, but about the numbers, we are still working on that.
Okay.
I should not say what is the false positive rate and things like that, but it is looking good.
Okay.
Any questions online?
Ariane?
Can you talk a little bit about the open questions, challenges in statistics and computation side of your work?
Oh yeah. Yeah, so I can talk about the things that I have been working on recently, which is here. So the problem with galaxies is they're this great unit high resolution to resolve them. So even this underlying truth I have here for one of the simulations, it is noisy. Like when you're counting how many galaxies you have, because of the Poisson error, it gets noisy. So yeah, so previously we didn't have that issue for light power spectrum. It was smooth enough. We didn't have too much Poisson error. Now the challenge I have here is somehow incorporate this in this, which shouldn't be like that hard, because probably we can from Gaussian process we know we can have error bars here, right? Then your the kernel you're learning incorporates the uncertainty you have on each data point. But this is something that I've been working on lately, and it seems like it is a little bit more challenging working with galaxies. But about like bigger open questions is we need to have even like bigger boxes for Lime Alpha Forest. You have these guys. This is one dimensional information. But if you're losing a lot of information, but not cross-correlating different sidelines. So when you want to calculate the theoretical correlation function, you need to have even a larger box. And even with this multi-fidelity technique, it is not that obvious for us if we can just expand to go to even bigger boxes to be able to model this theoretical correlation function. So so multi-fidelity helps, but still you need to have bigger simulations. Probably we need to just like improve the speed of our simulation, so we can just run.
Can you run instead of binary situation, multi-fidelity high and low, have a more continuous regime?
Like
Fidelity.
Oh, I see. Yeah, like having
One simulation that is a huge box, couple of simulation at the lower resolution. You keep lowering your resolution as you go to the whatever, instead of binary situation, low versus high.
Yeah, that's a great idea. Actually, we have not thought about that. Yeah, you could have different levels of fidelity, basically sampling from the scale. Yeah, that's interesting.
Do you always train more on low fidelity models than high fidelity models?
You mean the number of simulations?
Yeah.
Oh yeah, they're like very different. Maybe I have a number here. Yeah. So we have around like 2,300 low fidelity here and only 36 high fidelity.
That the low fidelity ones are more useful, or is it harder to come up with high fidelity ones?
High fidelity here, we can't compare how expensive they are to run. So this one is no hour. You need to compute one of the high fidelity one, and this one is the low fidelity. So it's very different. So these low fidelity ones are basically just exploring the parameter space to see how it is cosmology changes your observable. And the high fidelity one, you need enough of them to correct for the resolution.
So at the beginning, you brought up a problem that concerned you, which was the confusion between models. Failure due to model, the underlying model failure due to not being able to accurately model the systematics. And I think, so if you found a solution to that, particularly with respect to HETDEX data, where the data already don't have a lot of systematics there, like what is your approach to deal with that?
Yeah, so instead of doing likelihood-free inference, we are doing emulation, right? So here we have things like this. This shows how accurate your emulator is in predicting the truth. So we can do the same thing for the galaxy clustering. And then about the covariance and like whatever systematics we have with the observation, that's going to be on the data side. So at least we know, okay, my emulator is good enough to do a good job for theory. Then the data side and covariance side is something else.
Right. If there are no more questions, no questions online, let's thank Mahdi again.